Hi, everybody. Welcome to lecture 2.2, the second lecture of our unit on carbon capture, utilization, and sequestration. Today, I'm going to take you through some of the thermodynamics that underlie the process of carbon capture. I'll teach you some of the fundamental concepts of thermodynamics, nothing too crazy, just enough so that you understand what's going on here. And we'll talk about how that's applied to capturing carbon dioxide from a gas stream. So the general idea behind carbon capture is that let's imagine that you want to start trying to remove carbon dioxide from the atmosphere. So here on the left, again, we've seen a similar plot before. This is a plot of carbon dioxide concentration in the atmosphere in parts per million. That's what this gray line is. We've got time here on the x-axis. And then on the other y-axis, this is a bar graph each year of the difference from the 20th century average temperature. This is an anomaly in degrees Celsius. And again, you can see that the magnitude of that difference really tracks with the atmospheric carbon dioxide concentration. And I hope we all understand why that is at this point. So how are you going to start removing some of this carbon dioxide from the atmosphere? And even better, how can you prevent carbon dioxide from entering the atmosphere from something like a power plant? Do you have like a giant vacuum like this or what? So let's think about this. So you can do this really in two ways. You can either capture the CO2 at its point of generation, so something similar to that vacuum cleaner that I just showed, or you can just capture it from the air. This is sometimes called carbon removal. This is sometimes called direct air capture. We'll talk about some technologies to do that in a couple of lectures. But either one of these, fundamentally, you are taking a mixture of gases and separating one of the gases, namely carbon dioxide, from the other ones. So we're going to treat this in a very simplistic sense where we consider an incoming stream of gas. This could either be air just from around you, or it could be the flue gas coming out of a power plant from the combustion process. And we'll imagine that it consists of two different types of gases. Okay, and what we're doing is we're taking that mixture of gases and we're separating it. So we're taking a relatively disordered system and creating some order to it where we've got one gas on one side and the other gas on the other side. So let's talk a little bit about thermodynamic definitions before we really get into the nitty-gritty here. So there's four quantities that I want you to be aware of. They're heat, work, enthalpy, and entropy. Okay, so heat, I think we all intuitively know what heat is. It's, stuff that makes you hot. But the thermodynamic definition is that it is a mode of energy transfer to or from a system by virtue of contact with another system at higher or lower temperature. Okay, so you put a pot on the burner of your stove. The burner is hot, the pot is cold, the pot will heat up. Okay, heat is being transferred. Same thing if I take that hot pot and put ice cubes in it, the pot will cool down and actually the ice cubes will heat up also. So there's heat transfer going on there. Okay, now work is any other mode of energy transfer besides heat that changes the energy of a system. Okay, so these can include chemical reactions, raising or lowering a weight, turning on an electrical generator. Okay, any method of transferring energy that doesn't involve heat transfer. Okay, now enthalpy is the total heat content of a system. And entropy is the amount of disorder in a system. Okay, so that's our definitions of the quantities that we're working with here. Now, there are two laws of thermodynamics. Okay, actually, yeah, don't at me. I know there are three. There is the 0th law. We're not going to talk about that. We're going to talk about the first and the second law. That's I just used diuresis there. Did you hear that? I said we're not going to talk about the 0th law, and I just talked about it. It's kind of like we don't talk about Bruno. Anyway, the first law of thermodynamics is, or it's not diuresis, it's apophasis. Diuresis is the thing that looks like an umlaut. Anyway, you guys got me off on a tangent. Come on, you got to stop me when I do that. Okay, first law of thermodynamics is that energy is conserved in any process involving the exchange of heat and work between a system and its surroundings, okay? This is generally known in physics as conservation of energy. So you can't be creating energy, you can't be destroying energy. It has to be conserved in such a process. The second law involves entropy, and this means that the combined entropy of a system and its surroundings always increases. And if we go back a slide, entropy is the amount of disorder in a system. So a higher level of entropy means that there is more disorder in a system. So in general, if you combine a system and its surroundings, the entropy of that combination always has to increase. It always goes towards a state of further disorder, okay? Sometimes this concept is referred to as the arrow of time, because as far as we know, there's no way of going backwards, okay? If you scramble an egg, no amount of stirring is going to unscramble, okay? It's going from a very ordered state, yolk plus white, to a very disordered state, scramble, okay? So let's keep that in mind. That's the second law of thermodynamics. Okay, so back to our gas separation. So we're going from a mixture of two gases to two gases separated in a particular system. So the first question is, can this process happen spontaneously? And the answer is no, and that's because of the second law of thermodynamics, okay? You can't just expect the gases to sit there and spontaneously separate and be separated, okay? Now, just due to random motion of the gases, yes, you could briefly, instantaneously have this situation happen, but it will not be a stable state. The combined entropy of this system and its surroundings always has to increase. And so the lower entropy state obviously is going to be this one because it's a more ordered state than this. So if we consider a process that's going to go from high entropy to low entropy, we need to combine this system with some surroundings here where you're going to balance this reduction in entropy with an overall increase in entropy in the surroundings, okay? So to do that, we have to do something to the system, something thermodynamic. Okay, it requires work, okay? Not just work in like, gosh, this is hard work sense, but also in the thermodynamic sense, okay? So let's consider an idealized gas separation scheme. So we've got an input gas stream. So, let's imagine this is the flue gas coming out of a power plant. So we've got a flux of this stream. So it's total moles per second coming in. And we've got a particular mole fraction of CO2 in the flue stream, okay? Now, we want to put this through our magic gas separating box where we have an exhaust stream, which is going to be depleted in CO2. Ideally, it's going to contain no CO2, but I'll show you at the end of the lecture that that's not really possible. And so that'll have some flux and some mole fraction of CO2. And then we'll have the captured stream, which will be mostly CO2. Again, not pure CO2, but mostly CO2 with a flux of N cap and a mole fraction of CO2 of X cap. Okay. Now to separate that, we need to do some sort of work. We can have, a hamster running on a wheel. We can have, some tiny little horses pulling a string or something. But we have to do something in there because as we just saw, we are decreasing, the entropy of these two gas streams is lower than the entropy of the incoming gas stream. So something's got to happen in there involving work. Okay, now we also have to obey the first law of thermodynamics, okay, or else we have to go to thermodynamic jail, which is an unpleasant place. And this means that energy has to be conserved. So when we talk about energy, the change in energy, which we're going to call delta E, has to be the sum of the heat transferred to the system by its surroundings. So we're going to call that Q. And then the work done on the system by its surroundings. So we're going to call that W. Okay. So delta E equals Q plus W, heat plus work. Now let's briefly digress on different types of energy you can think about. So there's really three of them. There's what we call internal energy, which is usually denoted by the letter U. And then there's kinetic energy, which generally refers to the energy of motion, so how fast something is going. And then potential energy, which refers to the energy due to the position in some sort of a potential field. For example, in a gravitational field, my laptop is sitting on my desk right now. It has higher potential energy than if it were sitting on the floor. okay? And I can harness that potential energy if I throw it on the floor, which I'm not going to do to it, but that's what we're talking about here. Actually, that would turn the potential energy into kinetic energy. Okay, now here's how we can change these different types of energy. So we can change the internal energy by changing the temperature, by changing the phase, so the state of matter, solid, liquid, gas, plasma, Bose-Einstein condensate. We can do some kind of a chemical reaction, or we can even change the atomic structure. So, something like, fusion or fission or that sort of thing. Particle accelerators do this. Kinetic energy, obviously, we need to change the system velocity to change that. And then potential energy, like I just said, you're going to change its location in some kind of a force field. Okay, now, just like there's different types of energy, there's two flavors of work that we have to worry about. There's what's called pressure volume work, or sometimes this is called PV work. And this is work that is done just by the system changing its volume. So for the system to change its volume, it's got to, push away the stuff that's surrounding it to make room for itself. Okay. So, think about the Incredible Hulk ripping off his shirt. Okay. He's got to make room. He's doing PV work when he rips his shirt off because he has to make room for those big muscly pecs, right? Okay. So that's PV work. And we can represent that with an integral, that the PV work, you're just integrating over the volume change along a particular pressure path. Okay, so that's all that is. The other type of work is what's generally referred to as shaft work, and it's really just a catch-all for anything that's not PV work. But this is like, work that is done to rotate a shaft, like in a steam engine, or electrical work or that sort of thing. So you're not changing pressure or volume, you're doing some other kind of work. Okay, now let's talk a little bit more about entropy. So Ludwig Boltzmann and then later Max Planck came up with the definition of entropy. It's represented by the letter S, and it's K times the natural log of omega. So K is just a constant, which is called Boltzmann's constant. It's got this value here in SI units. And capital omega, that's the total of number of possible configurations of the system. Okay, so we'll talk about what that means with respect to our gas mixture in a little bit, but it's looking at the number of different ways the different components of the system can be arranged. Okay, now, as we saw earlier, second law of thermodynamics states that a change in the energy state of the system is only allowed if the overall entropy of the system and its surroundings increases. Okay, and entropy can only increase with time. It's not time reversible. And, this is still something that, you can read a lot about in the popular physics literature. This is probably a consequence of energy dissipation following the Big Bang. And, what's kind of interesting to think about is that eventually, many trillions of years from now, when energy completely dissipates, you talk about this concept of heat death, the universe will asymptotically reach a state of maximum entropy. And when this happens, it's possible that you won't be able to distinguish between time moving forward and time moving backwards, because there'll be no entropy to give you an arrow of time. So anyway, think about that when you're trying to go to sleep at night. Anyway, here's just an interesting aside. This is Boltzmann's tombstone in Vienna, and he actually has this equation on his tombstone, except he used W instead of omega to represent the number of possible states of the system. And he did that because it stands for a German word, Wahrscheinlichkeit, which means the probability of the occurrence of a macro state. And so we use capital omega now, but that's it. He also did something here, which this is one of my pet peeves, which is using log when you should be using ln. Okay, either say log 10 or say ln. Don't just say log, because then we don't know if you need that 2.303 figure in there or not. Okay, so anyway. Okay, so how does entropy relate to heat and work? Okay, so let's imagine a completely reversible process where you're going from one state to another. And by state, I'm referring to a temperature, a pressure, or a different composition. So remember that composition is what we're going to be working with our gas separation. A reversible process refers strictly to a minimal deviation from thermodynamic equilibrium. And you can think of this as being an isothermal process, right? Temperature is constant. Okay, so during this process, let's call the amount of heat transferred to or from the system Q rev to represent reversible heat transfer. Okay, so to get the change in entropy associated with this, so we'll call this delta S, and it's the entropy at state 2 minus the initial entropy at state 1. This is the total heat transferred divided by the temperature. And you can integrate this over the heat transfer path with this formula here. And you'll notice that I'm using a different delta here than just a D for a typical differential to represent that this is actually path dependent. And so the interesting thing is that this delta Q is path dependent. I'll explain what this means in a minute, but the change in entropy is actually independent of the path. And so because of that, we can always write using this expression here, if we just move the T over here, that the reversible heat is equal to the temperature times the change in entropy, okay? And that doesn't matter what path you take. Now, what do I mean by path? Okay, so let's again imagine an isothermal process. We've got no change in kinetic and potential energy. We're not doing any shaft work, okay? So what this means is that the amount of heat transferred is equal to the pressure volume work, and we saw this definition of PV work earlier. Okay, now if you think about traversing a particular trajectory in PV space and integrating the pressure along that path, if we start here at state A, so we've got volume on the x-axis and pressure on the y-axis, we can take many different paths. So for instance, we can take path 1 here, where pressure and temperature vary, pressure and volume vary till we get to point B. We can also get there by taking a different path. Okay, and when we integrate the pressure, so we're just integrating just means you're finding the area under the curve, right? So if we integrate the area under path 1, it's going to be this purple shaded area, and it's going to be larger than if we integrate the area under path 2. Okay, so that's what I mean by that this quantity is going to be path dependent. But the only thing that matters as far as entropy is concerned is the difference between these two states. Okay, and so that's really what we're talking about. It doesn't matter on how you get there. It just matters what the actual difference is between the initial and the final state. Okay, so that's a lot of basics and background on thermo, but let's talk about the work that's actually required to separate gas. So going back to our first law of thermodynamics, we're assuming that this is an isothermal process. And so that means that the we can, in general, well, let's work up to that. Okay, so we start off with first law of thermodynamics. Total change in energy is equal to heat added plus work done. Okay, now we can expand that into the different types of energy. So change in internal energy plus change of potential plus change in kinetic energy is equal to heat added plus work done by the system, that's shaft work, minus work done to the system, which is PV work. So done by the system versus done to the system is why we have the difference in the signs there, okay? Now, isothermal process, we're not changing potential or kinetic energy, so we can drop all these terms and just say that delta E is going to be this stuff that was on the right-hand side, and let's just combine all the work into a generic work term, okay? So this basically takes us back up to where we started, but we're just defining delta E as going to be delta U. Now, because this is isothermal, we can replace the Q term with T delta S. So we can write this in terms of entropy. And then again, potential and kinetic energy aren't changing. So let's just set, and the internal energy is also not changing. So delta E is going to be 0. And that means that the work is going to be minus T delta S. Okay, so this is the minimum amount of work that's required to separate these gases without accounting for any kind of energy losses due to inefficiency. Okay, now let's figure out what's going on here. We're going to do a mass balance on the stuff going into our magic gas separating box and the stuff coming out. Okay, so the total number of moles coming in has to be balanced by the total number of moles of gas coming out. And then we can write a mass balance specifically for CO2. So we'll multiply the total number of moles by the mole fraction. So again, total number of moles of gas is conserved, total number of moles of CO2 is conserved. Okay, And you'll notice here that we're going to assume that this is a perfect separation so that the captured stream only consists of CO2. Okay. Now, in reality, we can imagine that there is still some CO2 in the exhaust stream. So the captured stream is only CO2, but we're not capturing all of it. So we can define this parameter alpha. It's the fraction of CO2 that's captured. So it's number of moles of CO2 in the captured stream relative to the number of moles coming in the flue gas stream. And this means that the number of moles that's captured can be represented by this formula here. So you can think of this as a capture efficiency. Okay, so we're going to perform some substitutions back in our two mass balance equations here. And so we end up with this expression here for the exhaust stream. And then we substitute that into our second equation. And we see that the number of moles of CO2 in the exhaust stream is going to be given by this formula here in terms of the incoming mole fraction and then our separation efficiency. Okay, so we'll work with this equation in a little bit. Now, to figure out the amount of work we need to do, we need to figure out the entropy. Okay, so entropy is additive. The entropy coming out is going to be the sum of the entropy of the captured stream and the entropy of the exhaust stream. Okay, so that's the total entropy going out. And the change in entropy is simply the difference between that and the entropy coming in, which is our initial state, right? So delta S is entropy out minus entropy in, and then we substitute back the exhaust and captured stream here, and we get this equation here. Now, what are those individual entropy terms? Well, we can write those in terms of the total number of configurations in the system by utilizing this equation here, okay? So let's imagine separating CO2 from another gas like nitrogen in a process that yields 100% separation. So, forget about inefficiencies right now. So if we imagine we've got blue is the CO2 and yellow is the nitrogen. So here's the initial state. We've got nitrogen and CO2 molecules randomly arranged. Let's imagine that they're on some sort of a cubic lattice. And then when they come out the other side, we only have nitrogen in the exhaust and we only have CO2 in the captured stream, okay? So the total number of ways you can arrange the CO2 and nitrogen molecules here, okay, which I'm going to represent by the number of nitrogen and number of CO2, if they're equal to each other, then this is simply, combinatorics here. So it's the factorial of the total number of molecules divided by the product of the number of the factorial of both numbers. Okay. Now, in the exhaust and captured stream, there's only one possible configuration, right? Which is where all of these sites are occupied by either nitrogen or CO2. Okay. So what this means is that in the exhaust and the captured stream, the entropy is actually 0 because this is a perfect separation. So you take the natural log of 1, it's 0, multiply that by Boltzmann's constant, still get 0. So those are both 0. And we don't know what this term is over here. We're going to have to figure out a way of computing these factorials, okay? But what we can write here is we can substitute the captured and the exhaust, those are both 0. So the change in entropy is simply minus k times the natural log of this term here, all right? Now, we're going to use something called Stirling's approximation to actually turn this into something useful, all right? It's very hard to calculate these factorials because the number of molecules present, they're probably really big numbers, okay? So let's figure out a way of approximating this. So if you think about the natural logarithm of a generic factorial, which we'll call x, okay? So that's the natural logarithm of x times x minus 1 times x minus 2 times blah, blah, blah times 2 times 1. And then because of the product, properties of logarithms, since we have a product in here, this is going to be equal to the sum of the natural log of each term. So ln of x plus ln of x minus 1, blah, blah, blah. And we can represent this just by a sum. So this is going to be equal to the sum of ln of k, where k goes from 1 to x, okay? So here's the formula we just derived. Now, for sufficiently large x, we can actually write this discrete sum as an integral, okay? So we're integrating the natural log of k with respect to x, or going from 1 to x, I'm sorry, with respect to k. And this is easy because this has an analytic solution. So it's k ln of k minus k, and we'll evaluate that between 1 and x. And so we get this expression here. And because we're assuming that x is very large, okay, x is going to be much larger than 1. So we can drop the 1, it's approximately equal to this, this expression here, okay? So going back to our entropy terms, we can substitute that expression for these factorials of very large numbers by first specifying, we'll separate out the terms in the fraction over here due to the properties of logarithms, okay? And then we'll use our approximation for the factorial. So the math gets a little ugly here, but based on what I just told you, you can work through the algebra in your free time if you get bored. And what we come up with is that we use these two substitutions, and the change in entropy is given by this expression here in terms of natural logs. So this is called Stirling's approximation, and this is a good way of thinking about the entropy of the system, okay? So here's the entropy in terms of number of molecules. Now we can recast this in terms of mole fraction. So instead of n, we're going to use x. So x is the flue gas mole fraction of CO2. So assuming we only have two components present, x flu is the mole fraction of CO2, and 1 minus x flu will be the mole fraction of nitrogen. So we can work through this and multiply out some of the negative signs. And this tells us that the change in entropy is given by this expression here for perfect separation. So it's given as a function of the mole fraction of the incoming flue gas stream. This is Avogadro's number, which is necessary to convert from mole fraction to actual number of molecules. Okay, so to figure out the work, well, remember that the work is minus T times delta S, and delta S is going to, capital S is going to be the flux of incoming gas in moles per second multiplied by small delta S. And so this gives us this expression here, and we can make this a little bit easier on ourselves, and we can normalize this with respect to the work done per mole. So we'll divide this by x flu times n flu, which is just the work per mole. And so we get this expression over here, which again is just in terms of the incoming concentration and the temperature. And so you can plot this, so you can see how much work is required to separate CO2 from an incoming gas stream with a particular mole fraction, okay? So immediately what you notice is that it takes a lot more work to separate the CO2 if your incoming mole fraction is very small. And what's important to note here is that you can compare the amount of CO2 in power plant exhaust streams to that present in the atmosphere. So you'll see, depending on the different type of power plant you're dealing with, we've got natural gas combined cycle, post-combustion capture, usually used with a coal-fired power plant, and then integrated gasification combined cycle. You know, you're typically looking at less than, fewer than 10 kilojoules per mole of work required to separate. Now, if we look way up here, the amount of CO2 in the air, it's a very, very small mole fraction. I know that, the numbers get thrown around, 420 parts per million or whatever, sounds scary, but compared to the exhaust stream from a power plant, it's very small. And it takes a lot of work to separate CO2 directly from the air. So when you read about these direct air capture technologies, you have to remember that this is a thermodynamically very unfavorable process. And so there's a lot of innovation that is currently going on to be able to make this work at scale. And it's very exciting to see some of this happen. Capturing CO2 from a power plant is comparatively easier. Okay, so all of our analysis right up till now has assumed that we don't have any energy loss. But indeed, when you're actually doing this for real, you have to worry about energy penalties and parasitic energy. So energy penalty really refers to CO2 capture from a power plant. And generally, you're going to take some of the power plant output and use it as the energy that's required to do the separation. So your energy penalty, that's just the fraction of the overall power plant output that's going to your CO2 separation. And the parasitic energy, once you separate the CO2, you need to compress it to be able to use it later. And so that's just going to be the sum of the separation and the compression energy. All right, so remember those definitions moving forward. Here's a plot of energy penalty as a function of the percent of CO2 captured for different concentrations in the incoming gas stream. So again, what you notice is that as you increase the concentration in the incoming gas stream, it takes less energy to separate it, which we just showed that with thermodynamics. But generally, for these types of concentrations, if you're going from 80 to 100% CO2 capturing, you're going to use anywhere from like 3.5 to maybe up to 6% of your total power plant output just to capture, just to capture that CO2. This doesn't include compression. So, when you're designing these types of facilities on power plants, you really have to balance how much energy you want to put into it versus, how much of the CO2 you actually want to capture. Okay, well, thanks for hanging with me through all of that thermodynamics. Next time, I'm going to talk about the different methods that we have of carbon capture and how they work.